What if the universe's deepest secrets aren't locked away in complex equations, but revealed in bee dances? These creatures navigate by the stars, seemingly predict the future, and they waggle. It's a hidden code, a biological algorithm echoing throughout the cosmos. Imagine a world alive with whispers, where the very essence of existence is entwined with the delicate ballet of bees. The honeybee, Apis mellifera, a creature diminutive in size, yet monumental in its impact, pollinating a significant portion of the food we consume, a service worth billions annually. But their true significance may extend far beyond sun-drenched orchards and bustling hives, revealing fundamental principles of information transfer. Within the intricate society of a honeybee colony, sometimes swelling to tens of thousands, lies a marvel of natural communication: the waggle dance. A precise, rhythmic performance used to pinpoint the location of precious food sources. Carl von Frisch unlocked its secrets, earning a Nobel Prize, which he shared with Konrad Lorenz and Nikolaus Tinbergen for their discoveries concerning the organization and elicitation of individual and social behavior patterns. Back in the hive, the dancer meticulously traces a figure-8 pattern. The crucial element: a straight waggle run bisecting the figure. The angle of this run, relative to the vertical, mirrors the angle of the food source relative to the sun. Distance is also encoded with remarkable accuracy, even for sources several kilometers away. A faster waggle signals a more abundant reward. But this is more than mere insect choreography. Recent studies suggest that electromagnetic radiation and pesticides may be disrupting this ancient language, contributing to the alarming phenomenon of colony collapse disorder. If these tiny creatures can encode and transmit complex spatial information with such apparent ease, what other secrets might they hold? What if the principles governing their navigation, their communication, echo patterns found throughout the cosmos, woven into the very architecture of reality itself? Before we unravel this buzzing mystery, what springs to mind when you think of bees and secrets? Subscribe, and let's explore together. Within the hive's bustling metropolis, a forager emerges, returning from her quest. She launches into a captivating ritual upon the comb: the waggle dance. This isn't just movement, it's a sophisticated language, a biological algorithm transmitting vital coordinates with astonishing accuracy. The key to unlocking this dance lies in three crucial elements: distance, direction, and the prize itself, the quality of the nectar discovered. The distance to the food source is meticulously encoded within the duration of the waggle run. For every second the bee waggles her abdomen, approximately 75 meters are added to the journey. Picture this: a microscopic messenger, calculating and conveying vast distances with such remarkable precision. Direction, the precise bearing to the floral bounty, is etched into the dance through a celestial reference point: the sun. The angle of the waggle run, relative to vertical on the honeycomb, mirrors the angle between the sun and the food source. Bees, with an innate understanding of celestial navigation, translate sunlight into spatial awareness. Even under cloudy skies, they harness polarized light, invisible to our eyes, to maintain their orientation and relay accurate directional information. The quality, the desirability of the reward, is communicated through the sheer intensity of the dance. A more vigorous waggle, accompanied by a louder, more insistent buzzing, signifies a richer, more abundant food source. This isn't merely a map, it's a recommendation, a glowing review of the floral offering. The hive mind, collectively assessing the value of its resources. The waggle dance isn't pure instinct, however. It is a learned behavior, passed down through generations of foragers. Young bees, apprentices in this intricate language, observe and mimic the dances of their elders, gradually mastering the nuances of its complex grammar. They learn to decode the movements, the angles, the vibrations, transforming abstract signals into actionable knowledge. The hive becomes a school, a living library of floral intelligence, constantly updating its knowledge base and ensuring the colony's survival. Imagine, for a moment, seeing the world through multifaceted eyes. Our forager launches skyward, propelled by primal instinct and encoded instruction. 8 kilometers, the potential reach of her mission, a distance that, for her, is nothing short of an epic undertaking. She ascends, instantly orienting to an invisible grid etched across the sky. Polarized light, a celestial map readable only to her kind, guides her even when veiled by cloud cover. But the air is a turbulent sea, the wind a constant adversary. A 15-mile-per-hour headwind doesn't merely slow her, it leaches vital energy, doubling the caloric cost of her quest. Each wing beat is a desperate calculation, a constant correction, a plea to maintain her course. Unseen dangers lurk. A flash of iridescent green, the bee-eater, a feathered predator with a deadly taste for honeybees. A dragonfly, a silent hunter, patrols the air currents with lethal grace. And then there are the pesticides, an invisible threat clinging to the very blossoms she seeks, a deadly reward for her diligence. Her lifespan, at its absolute peak, a mere 3 to 6 weeks, an ephemeral existence fueled by relentless, tireless labor. And the prize? 2 million flowers must surrender their nectar to create a single pound of honey. A staggering equation of effort and reward. This perilous journey, repeated countless times, is not simply about sustenance, it's about information translated from the dance, a complex algorithm guiding her across a vast and hostile world. Mathematical marvels lie hidden within the seemingly simple waggle dance. More than just a language, it's a sophisticated algorithm in motion. At its heart, the dance encodes the direction and distance to a food source, employing principles akin to vector calculus. The angle of the bee's central waggle run, relative to vertical on the honeycomb, mirrors the angle of the food source in relation to the sun. This isn't mere instinct, it's a living compass, etched in movement. The duration of that waggle speaks volumes. Each second equates to approximately 75 meters of flight, a longer waggle signifying a richer, more distant reward. Carl von Frisch, who ultimately unraveled this intricate system, dedicated years to its decipherment, a testament to the hidden complexity within. Awarded the Nobel Prize in 1973, his groundbreaking work revealed a world of insect communication previously unimagined. Researchers now model the waggle dance as a real-world optimization algorithm. Imagine bees collectively exploring a landscape, each sharing snippets of vital information through their dances. This shared knowledge, this collective intelligence, guides the hive towards the most efficient, the most rewarding food sources. The process mirrors algorithms like particle swarm optimization, used in computer science to solve incredibly complex problems. Consider the fascinating pollen isograde phenomenon. Bees don't simply follow a static, fixed map. Instead, they dynamically adjust their foraging ranges based on fluctuating food availability. If a nearby patch dries up, the dance language subtly shifts, directing foragers further afield, optimizing resource collection in real time. The precision of this intricate communication has been rigorously tested and validated. In a landmark study by Riley and colleagues in 2005, harmonic radar was used to track individual bees. The results were astonishing. The waggle dance accurately conveyed distance and direction information over several kilometers, confirming the dance's remarkable accuracy. Deborah Gordon's insightful work on ant colonies reveals intriguing parallels. Just as bees use the waggle dance, ants employ sophisticated trail-laying and communication strategies to coordinate foraging. These shared principles of distributed information processing in social insects hint at a broader, more fundamental principle at play, suggesting that the very fabric of the universe may be governed by similar principles of optimized information transfer. The vector algebra woven into the waggle dance, a language of direction and distance, finds an echo in the grand symphony of astrophysics. Galaxy formation models simulating this cosmic ballet, powered by intricate n-body simulations and smoothed particle hydrodynamics, strangely mirror the bee's own optimization strategies. Gravity, like the bee's relentless search for nectar, guides the system toward a delicate equilibrium, sculpting order from the swirling chaos. Seemingly disparate, both processes hum with algorithms striving for the most efficient configuration. Quantum annealing, a technique employed in the cutting edge of quantum computing to discover the global minimum of complex functions, resonates with the bee colony's tireless quest for optimal food sources. Both navigate a labyrinthine solution space, tentatively testing possibilities, and ultimately converging on the most rewarding outcome. The quantum realm, like the diligent foraging bee, explores a landscape of probabilities to pinpoint the sweetest spot. Even the digital networks that bind us together globally bear the subtle imprint of bee behavior. Routing algorithms, particularly those inspired by ant colony optimization, ACO, directly emulate the foraging strategies of social insects, and the elegant waggle dance. ACO uses probabilistic methods to chart the shortest paths between nodes in a network, mirroring the bee's collective intelligence in mapping the most efficient routes to life-giving resources. The extraordinary efficiency of the waggle dance in solving distributed optimization problems has been rigorously compared to established computer algorithms designed for similar tasks. These revealing studies demonstrate that bees, through eons of evolution, have perfected a profoundly effective system for distributed information processing and resource allocation, a system whose fundamental principles reverberate in the very fabric of the universe itself. Picture the waggle dance not just as a peculiar bee ritual, but as a living, breathing algorithm. Imagine it as a set of instructions, meticulously encoded in movement, translating directly into purposeful action. In 1973, Dr. Carl von Frisch deciphered this remarkable code, revealing that the dance's angle, duration, and intensity are precise metrics, communicating the distance, direction, and richness of vital resources. Scientists have discovered that algorithms modeled on bee foraging, particularly particle swarm optimization, PSO, can simulate systems of staggering complexity, such as galaxy formation. By inputting the fundamental laws of gravity and the initial distribution of matter, the algorithm, mirroring the bee's tireless search for nectar, iteratively refines the positions and interactions of simulated particles. Breathtakingly realistic spiral galaxies emerge from the digital dust, structures that faithfully mirror the cosmos, born from an algorithm that echoes the humble bee. Even the esoteric realm of quantum computing bends to this biomimetic approach. Quantum computers manipulate qubits, the fundamental units of quantum information. Optimizing the intricate configurations of these qubits presents a monumental challenge. Once again, PSO offers a solution. By treating each qubit configuration as a potential food source, the algorithm efficiently navigates the vast quantum landscape, seeking the optimal arrangements for performing complex calculations. The efficiency of this system is paramount. Bees recruit more foragers to higher-calorie food sources. This direct proportionality, a quantifiable relationship between caloric value and bee numbers, reflects a fundamental principle of resource allocation, a principle that resonates even in the most abstract computational problems. A 2016 Nature Communications study revealed that collective bee behavior exhibits self-organized criticality, a hallmark of complex systems operating near a tipping point. This criticality empowers the colony to respond rapidly and efficiently to environmental changes, showcasing a level of adaptability that mirrors the resilience of the universe itself. The dance of the bees, it seems, is a microcosm of the grand cosmic dance. The hive mind. The term itself conjures images of a unified intelligence, an emergent property of social insect colonies. While popularized, the concept hints at something far grander than mere instinct. A solitary bee makes perhaps a dozen decisions each day. A colony of 40,000 bees executes a staggering 12 million decisions daily, a feat of decentralized computation that boggles the mind. This collective intellect takes shape, in part, within the mesmerizing waggle dance. The angle of the waggle, relative to the sun's direction, speaks volumes. The duration of the waggle conveys distance. The intensity, quality. A sophisticated code, readily deciphered by fellow foragers. Researchers at the University of Sussex discovered that bees utilize the waggle dance not only to pinpoint food sources, but also to collectively decide on new nest sites. Through this intricate communication, the colony often converges on the most optimal location, even if no single bee has individually explored it in its entirety. It's a distributed search algorithm, organically evolved over millennia. Consider the work of Thomas Seeley at Cornell, revealing a fascinating phenomenon: quorum sensing. Before committing to a new home, a critical mass of bees must reach an agreement. A threshold is crossed, a decision solidifies, and the swarm moves as a single, unified entity. A collective consensus, self-organized and remarkably efficient. Deborah Gordon's research on ant colonies at Stanford demonstrates that these diminutive creatures, through simple interactions and the strategic laying of pheromone trails, collectively solve incredibly complex problems. Foraging routes mapped out, nest construction completed, all accomplished without any central command or overseeing architect, just the emergent intelligence of the many. Are these merely examples of simple creatures performing simple tasks, or are they manifestations of something far more fundamental about the very nature of intelligence itself? Is the universe, in its own way, also dancing? The hive, a marvel of decentralized intelligence, now confronts an unprecedented onslaught of threats. Colony collapse disorder can decimate entire colonies. The answer, it seems, is a complex tapestry of interwoven dangers. Neonicotinoid pesticides, engineered to safeguard crops, cripple a bee's cognitive function, turning its internal compass into a disoriented mess. The waggle dance, once a precise map to sustenance, becomes a garbled message, a misleading path towards oblivion. Urban sprawl and relentless agriculture are erasing the vibrant tapestry of wildflowers and flowering trees upon which bees depend. This habitat loss triggers nutritional stress, weakening their immune systems and leaving them vulnerable to disease. Varroa mites, insidious parasites, further amplify the crisis. These mites, feeding on bee blood, act as vectors for deadly viruses, most notably the deformed wing virus. A single mite infestation can cripple an entire colony, transforming healthy bees into flightless shadows of their former selves. The delicate synchronicity between flowering times and bee emergence is unraveling before our eyes due to climate change. Flowers bloom too early or too late, leaving bees stranded, their foraging patterns disrupted, the waggle dance rendered useless by a world out of sync. The Asian hornet, a relentless predator, descends upon hives, tearing apart the delicate social fabric. These hornets can decimate entire colonies in a matter of weeks, leaving behind a scene of utter devastation. The waggle dance, a symbol of collective intelligence, is replaced by the frantic buzzing of panic, a desperate plea for survival against overwhelming odds, a call to action we cannot ignore. The seemingly simple waggle dance holds surprising keys to solving some of humanity's most intricate challenges. Inspired by the bee's uncanny ability to communicate optimal routes, researchers have developed algorithms that mimic this behavior. Simulations reveal that strategically adjusting traffic light timing based on these algorithms can reduce congestion. The hive mind, that decentralized intelligence humming within the colony, has birthed swarm intelligence algorithms that are now deployed in robotics. This same principle underlies ant colony optimization, ACO, algorithms that now guide the flow of data through telecommunications networks, charting the most efficient pathways for information to traverse the globe. The hexagonal design of the honeycomb has inspired innovations in materials science and building design. Algorithms modeled on bee foraging strategies are being used in cloud computing to allocate resources, minimizing energy consumption and maximizing performance. The collective intelligence demonstrated by bees in choosing a new nest site is informing the development of prediction markets. The intricate dances of bees, therefore, are blueprints for a more efficient, more connected, and ultimately, more intelligent future. Can the secrets of the universe truly be hidden within the dance of a bee? Perhaps not entirely, but the possibility shimmers with a compelling allure. Carl von Frisch unveiled the intricate language of the waggle dance, revealing how these tiny creatures communicate direction and distance with astonishing precision. A single second of waggle translates to roughly 75 meters. Consider the bee's uncanny ability to navigate using polarized light, deciphering hidden patterns in the sky even when clouds obscure the sun. This hints at a capacity to perceive and process information in ways that resonate with our own most advanced technologies. Researchers are now actively exploring the waggle dance as a blueprint for swarm robotics. This swarm intelligence is already finding applications in diverse fields, from optimization algorithms to traffic management, and even financial modeling. However, this fascinating window into nature's secrets is under dire threat. Bee populations are in alarming decline, ravaged by habitat loss, the insidious effects of pesticide use, and the spread of devastating disease. Losing these creatures is not simply an ecological tragedy, it's potentially a catastrophic loss of invaluable knowledge. If the waggle dance offers a glimpse into the fundamental principles of information transfer and optimization, then protecting bees becomes not just an environmental imperative, but a profound quest for understanding the very fabric of the universe. The waggle dance, therefore, transcends its humble origins. It is a testament to the power of distributed intelligence, a living algorithm etched in the very fabric of life. Its echoes resonate throughout the cosmos, hinting at a deeper, underlying principle of efficiency and optimization that governs systems both biological and technological. While seemingly unrelated, the complex algorithms and communication methods employed by bees in their waggle dance share surprising mathematical and computational parallels with models used in astrophysics, quantum computing, and network optimization, suggesting a deeper, underlying principle of efficiency and information transfer at play throughout the cosmos. Does the bee's dance reveal a universal language of optimization, subtly whispering secrets of efficiency that echo from the quantum realm to the grandest scales of the cosmos?